Hello, my name is Tong.
I'm Ishaan, uh, and today I'm going to talk about random numbers. Randomness is all around us, uh, and we have this knack of spotting exactly what is random and what isn't random. But mathematically, it's hard to put into words exactly what is and what isn't random. So the first question we're going to be talking about today is, what does it mean to be random?
Well, that's a very hard definition to pin down. What exactly does randomness mean? We have no inherent mathematical formula to determine what randomness is. So to start off, we're going to be looking at a few examples of random and non-random events to help us figure out what randomness means. So an example of a random event, it's flipping a fair coin. If it's truly a fair coin, you have a half chance of either getting heads or tails, which means that it's random. Drawing from a well-shuffled deck, you have a 1/52nd chance of getting any card from the deck. There's no way to know beforehand. It's random. Rock, paper, scissors. There's only one strategy to play the game, and that's to play randomly. There's no other way to play it.
On the other hand, you have some non-random events. Uh, Bouncing a ball off a wall is non-random because there's only one direction the ball is going to go based on the trajectory, uh, gravity, and the angle. Um, Taking a test, likewise, it's not completely random what grade you're going to get because it depends on how much you studied, how much you slept, for example. Likewise, weather is not completely random. It's influenced by what the weather was on the day before, for instance, or the whole week, right? If it was rainy one day, then it's more likely to be rainy the next day. Um, so now, looking at all of these different examples, we see a common theme among the non-random events. If an event is influenced by external factors, then it's not random. If there's only one possible outcome, then it's not random. So using this idea, we can come up with this definition of randomness. An event is random if there are multiple possible outcomes whose probabilities are always the same. That is, no matter how many times you or where you do it, the probabilities of each of the possible outcomes will remain the same.
A related definition is a definition for determinism. So an event is deterministic if there's exactly one possible outcome. So the event is affected by what happened before it. There is only one possible outcome for the event.
Um, one of the reasons why randomness and determinism are so related is because um, randomness and determinism together, we can sort of describe the entire universe like this. For a long time, physicists believed that the universe was fundamentally deterministic, um, and that you could predict exactly what would happen if you knew all the rules. But in the early 20th century, with the advent of modern physics and quantum physics, we started to learn about how randomness is also a big part of the universe.
So now we talk about what randomness is. What are some uses of randomness in our lives? Well, for one, simulation. Nature itself, it's inherently random. It's too complex for us to simulate without any randomness. So we need randomness to simulate it. Statistical sampling. Given a population, you will need to take a random sample from the population to achieve good results. Otherwise, your results are going to be very biased. Cryptography. Everybody's heard of public key, private key encryption. You need random numbers to do encryption. Otherwise, everybody will be able to figure out your keys.
Another use of randomness is in computer programming. Algorithms that use randomness are often more efficient than their deterministic counterparts. Calculations as well, we can use randomness to approximate numbers that are difficult to calculate otherwise. And recreation, things like video games and online casinos need random numbers for their use. However, notice that most of these uses of randomness is most useful on computers for us to use calculations. And this leads us to our next question. How do we generate randomness on computers? Now, there are many ways to get randomness onto a computer, right? We can get randomness from a die, we can roll a die, we can hook it up to like a Geiger counter. But which are the most convenient ways but those aren't really convenient ways of getting randomness. It makes sense that we want random numbers since computers will work well with them. But classical computers are deterministic, which means that it is completely predictable what the next number in the sequence will be. Computers by themselves, we cannot generate random numbers with only computers. However, we can generate random-like numbers called pseudo-random numbers from computers, and this is what we're going to be talking about in these next few slides. However, we only have to determine what the distribution, what are the probabilities of each of the numbers now. And to do this, we'll talk about distributions a little bit first. So this is an example of a distribution. This would maybe be a model of situation where you have 3 red marbles, 2 green marbles, and 1 blue marble in a bag, and you're drawing out of them. To model this distribution on a computer, how do we go about doing this? Well, if our generator generated numbers based on this distribution, so like 0, 1, 2 with these relative probabilities, we could do that. Another way to notice is that you can break these up into chunks of equally likely blocks. So if we generate 6 different types of random numbers that are all equally likely, then we can set, for example, 0, 1, and 2 to red, 3 and 4 to green, and then 5 to blue. 0 and 6 excluding 6. So in this sense, it seems that the most optimal distribution for use on computers is the uniform distribution. That is, every number should be equally likely to be generated. One good, very common method of generating random numbers is called a linear congruence method. This method is pretty simple. We start with a seed, x0, and we choose 3 numbers: a, the multiplier; c, the increment; and m, the maximum. These are all integers. And this method works on every random number to get the next random number. So we use this formula. We're going to multiply the current number by a, add c, and take the remainder after dividing by m to get the next number. And given our choices of a, c now, we can actually get very convincing random sequences, pseudo-random sequences.
Another good way of generating random numbers are using cellular automatons. And one cellular automaton in particular that's really good at this is Root30. So how Root30 works. So first, you have a row of infinite white squares and you have a black square in between them. And by following a set of rules, these 8 rules listed here, you can generate every row after the first row, like so, and row by row, until you generate the entire diagram. And when you do, you can use the source of randomness, such as your system time, to take a particular part of the diagram, for example, a certain section of the middle column, and you can interpret that section of the middle column as a random binary number by using the white squares as zeros and the black squares as 1. So the next thing we're going to talk about is how quantum computers work and how they apply to generating random numbers. Well, first, instead of using classical bits, quantum computers use qubits. And what that means is that instead of being able to only represent the state 0 and 1 separately, a qubit can represent both states 0 and 1 together with varying probabilities when measured. And to visualize a qubit, you can use a block sphere, which is a 3D geometric representation for a qubit. And you can see the state of your wave function, the state of your qubit, by looking at where your vector is pointing to on the surface of your block sphere. So now we know how quantum computers work. How do we generate random numbers with them? Well, just like with normal computers having logic gates, quantum computers have their own kind of logic gates called quantum logic gates. And one of these gates in particular, the Hadamard gate, is a quantum logic gate that transforms a wave function from the state 0 to a wave function of 1/√2 of 0 and 1. And what that basically means is that when you measure the state of the qubit, when you observe it, you will get half the probability of getting 0 and half the probability of getting 1. And that's because the Born rule states that getting any eigenstate is equal to the square of its coefficient. So in our case, since the coefficients are 1/√2, we will get 1/2 chance. And so basically with n qubits, we will be able to generate an n-digit binary number. And since every qubit is random, whether it's 0, 1, truly random based on our current understanding of quantum physics, our sequence of qubits, our sequence of random numbers will be a truly random binary number as well.
Now, talking about these generators brings up the question of how do we determine whether a sequence is random or not? And there are various statistical tests that we can use to determine this. So we're going to be covering the Monte Carlo test, the chi-square test, and the Kolmogorov-Smirnov test. But there are other tests as well, and they use these basic tests.
So the first test we're going to be talking about is the Monte Carlo method. So what is the Monte Carlo method? It's a method of using random sampling to obtain deterministic results. What that means is that you use randomly generated numbers in order to find answers to your math problems. So for example, if we were to generate random numbers in the range 0 to 1, and then we interpret those random numbers as coordinate pairs and place them on the coordinate plane, we can then find the number of coordinates within radius 1 of the origin. And how would that be useful? Well, the probability of a point being in radius 1 of the origin is pi over 4. That's because an area of the quarter circle over the area of the quarter square is equal to pi over 4. And since we are able to get pi from this, we can see that the more uniform our distribution is, the closer our calculated value will be to pi, so the more random our numbers are. The second test we're going to be talking about is the chi-square test. And the chi-square test is used on two sets of discrete populations to see how closely related they are. So that basically just means you take two series of numbers and you see if they came from the same distribution. And if our random numbers were perfectly random numbers, they should produce something close to a uniform distribution. So to do the chi-square test, you have to determine the chi-square statistic. And the chi-square statistic is determined by the sum of the observed minus the expected squared over the expected. And what does that mean? Okay, so first, step one, you generate a large amount of random integers within the range 0 to m. And then you can calculate the expected value for each number. And in our case, it would be the total amount of numbers generated divided by the range in which you generated the numbers in. And you will fill in the expected in the equation with that. And using that equation from above, you can then determine the chi-squared value. And with the chi-squared value, you'll be able to determine the p-value with the degree of freedom being n minus 1 and n being the total amount of numbers you generated.
Another related test is the Kolmogorov-Smirnov test. And this is very similar, except it compares the data set to continuous distribution that may have generated it. So in this case, we're going to assume our theoretical distribution of our random numbers is uniform in 0 to 1. That means every number from 0 to 1, irrational, rational, no matter what, all of them will be equally likely. We're going to assume that. So for this test, we're going to have to define an empirical distribution function. And we do this from the data set. Our fn of x is equal to the number of data points less than or equal to x divided by the total number of data points. And we compare this to the cumulative distribution function, which is f of x is equal to the probability that a data point is less than or equal to x, right? Now, since every number between 0 and 1 is uniform and equally likely, this means that f of x will equal to x. And so using these two, we can plug this into the Kolmogorov-Smirnov statistic, which is Kn plus and Kn minus. And these basically tell us, measure the variance, the greatest variance, the greatest deviation between the two functions at any point. And using these two, we can use a table like in the chi-square test to calculate the threshold p-value to say whether the values that we get are too extreme or not. So in conclusion,
and then it's random if there's multiple possible outcomes whose probabilities are always the same.
some of the common RNGs that we talked about are the linear congruence generator, or the LCM, cellular automaton, and quantum computers.
And there's a variety of statistical tests that you can use to determine the randomness of a sequence of numbers. And that includes the Monte Carlo method, the chi-square test, and the KS test.
And Tong helpfully made a website for this randomness presentation, which you can check at either of these two links over there. And here's a GIF of him and his Minecraft LCG.